We present a system to enable multi-finger touch typing on any flat, uninstrumented surface using only a head-mounted stereo pair of cameras, as can be found on many consumer VR devices, including the Meta Quest 3. To initialize our system, a user sits at a table and holds up their hands to enable hand size calibration. They then place their hands on the table to calibrate the plane of the surface, after which a virtual keyboard appears. The virtual keyboard can be rotated or moved within the plane into a comfortable position for typing. The user can then place their hands on the virtual keyboard to type. The virtual keyboard has an industry-standard 19mm key pitch, so that typists can leverage muscle memory they learned from typing on physical keyboards for touch typing in AR or VR. Our approach emits characters as keys are hit by using a motion model to directly map hand motion onto typed text. We take images from the stereo pair of cameras on the headset, sampled at 30 Hz, and feed them into an egocentric markerless hand tracking system. We then feed the resulting hand poses into a streaming transformer-based motion model, which is trained to predict the keys a typist intended to hit. To allow this motion model to reason about occlusion, uncertainty, and high-frequency noise, which may contain valuable information but that is not captured in hand pose alone, a rich connection is added to expose latent features from within the hand tracking model as input features to the motion model. Training our motion model requires ground truth data consisting of hand motion paired with the sequence of keys that a typist intended to hit. For this, we stand up a closed-loop data collection system in which participants don a head-mounted stereo camera pair and sit in front of a touchpad keyboard. A monitor in front of the participant displays a prompt, which the participant then transcribes. The keys produced by the touchpad keyboard are displayed to the user and recorded as ground truth labels. And because people can naturally make and correct mistakes, our training data includes coverage of the backspace key as well. On virtual keyboards without the haptics of key edges, typists often over or under reach for their intended key, which we call slop error. We aim for our motion model to predict the key a typist intends to type, regardless of slop error. To this end, our touchpad keyboard is biased during data collection so that the next key a user should hit, according to the prompt, has a bounding box inflated to 4 times the normal key size. This allows participants to type naturally, and so long as they touch reasonably close to the right keys, we can label their motions with the keys they intended to hit, rather than those that they physically hit. This method of labeling training data was critical to achieving accurate predictions. We recruited 18 participants for a user study and found that people could type on average at 42.3 words per minute with 7% uncorrected error rate using our system, compared to a baseline of 74.8 words per minute with 0.8% uncorrected error rate on physical keyboards. Notably, this is without the benefit of a language model. For more information on our system and its evaluation, please see our paper.